All right, so let's start off with an example. In a reaction, 22.3 grams of sodium, which we sometimes write Na, completely reacts with 79.9 grams of bromine, which we normally write Br, to form some mass of sodium bromide, NaBr. And I want to know the mass of the product formed. Well, to do that, you normally need stoichiometry and some math. And you don't know that yet. You don't know about balancing equations and the way these chemicals interact and all the things that would normally be used here. But you do have a trick up your sleeve in this case, and that's the law of conservation of mass. And you happen to know that the mass of the reactants, that is the things that are there before, equals the mass of the products. As a matter of fact, this is the only thing you know about chemistry at the moment. Well, in this case, it's pretty easy. I've got some sodium, Na. As a matter of fact, I have 22.3 grams of it. And I've got some elemental bromine, Br. And I got like 79.9 grams of that. And I'm going to add these two things together because when I'm done, I get a new chemical called sodium bromide. And I get some amount of it. But in this case, isn't it true that my mass of all my reactants here, mass react, has to be equal to the mass of the bromine? Because there's no other chemicals sitting over here, right? I don't have anything else here. I'm only making the sodium bromide. So if I'm only making the sodium bromide, then all of the mass of the sodium and the mass of the bromine, they have to be combined together. Otherwise, I'm not getting anything. So, here I get something really easy. I get something like 79.9 grams plus 22.3 grams. That's going to be equal to like 102.2 grams. And a few of you might be like, oh, but Mr. Nedick, you don't have the right number of significant figures. Like, look, you got 3 here, and 3 here, and 4 here. Well, that's true. Except remember, this is addition. In addition, we only care about the decimals. So since each of my terms have 1 decimal, my answer needs to have 1 decimal. And so this is the correct answer, 102.2 grams. So if I carry out this reaction, which don't, by the way, it's terrifying, I'd end up with 102.2 grams of sodium bromide, ideally. Even if I didn't, because this doesn't make anything else, all the unreacted reactants, all the things that didn't turn into sodium bromide, the elemental sodium and bromine, would still be left in my reaction vessel, and the mass should still be 102.2. Let's take a look at a little bit harder one. Let's look at another one. 12.2 grams of methane react with 24.5 grams of oxygen, and that makes 26.7 grams of carbon dioxide and some amount of water. And my question is just how much water? And this question would be difficult, again, if I didn't have the law of conservation of mass. Because I do, it's pretty easy. Remember, the mass of my products equals the mass of my reactants. That is, the left and the right-hand sides have to be equal. Well, let's abbreviate methane with a big M and oxygen with a big O. And what's color code those? Those are my reactants. And I've got over here some carbon dioxide, let's just call that C, and some water, W. Now, of course, this isn't how chemists would actually write this. Like we'd say, what, CH4 and O2 and, CO2 and H2O. But you know what, let's just keep it simple. I've got these products and reactants turning into each other. Well, I know that this mass here and this mass here have to be equal, right? There's nothing else going on in this reaction. And I know I have over my methane, I've got 12.2 grams. And I know my oxygen, I have like 24.5 grams. And over here, I know I have 26.7 grams of my CO2. And I don't know how much water. Well, 12.2 plus 24.5, that's just 36.7 grams. And 26.7 plus X. You see how I've kind of set up a little algebra problem here. 26.7 plus my X. Well, that's easy to solve for, right? Because you just got to move this X to itself, or get this 26.7 to the other side. So I can take 26.7 grams away from both sides. And of course, I get down to something like 10.0 grams equals X. And That's it. So in this reaction, apparently we get 10 grams of water if it is done correctly. Now you might say, Mr. why'd you write the 0 here? Remember, this is subtraction. 3 sig figs here, 3 sig figs here. Doesn't matter really in this case. What matters is the number after the decimal. And even though I get 10 here, I need to add in that last 0 for the right number of sig figs because I had decimals in each case. So I know that 0.0 exists. Is that going to really matter on a test? Less so, right? What I really care about on a test is you knowing this. Is it going to matter on a homework? Sure. Because I want you to make sure you're still practicing with sig figs, so when we're in a lab, we're getting better at using these things. In general, these slides and these questions, they're not that terrible, right? It's just really simple algebra. You don't let the questions, because they're full of chemistry, scare you. This should be pretty straightforward stuff. All you're doing is kind of solving for x and making sure both sides of the equation stay equal. As long as you think of it like this, these problems will be easy and you can breeze right on through them. I've given you a little bit of homework over that tonight so you can try that out. And hopefully you'll find it pretty straightforward. If you get stuck, feel free to email me, but first try asking a couple other people in the room who seem to get it. Because that'll save me a little bit of time while I'm on Kairos. In the same breath, you'll get your answer right now instead of later tonight or tomorrow whenever I can answer it. So good luck. And I look forward to being here again tomorrow with you. We'll talk a little bit more about chemical properties.